Okay, to wrap up section 16.3, we're going to talk about an application of the fundamental theorem of line integrals to an important law in physics that you are probably familiar with, the law of conservation of energy. So to begin with, we're going to consider a particle with a mass of m moving along a path c that's given this parameterization r of t, and t is going to go from a to b. So this parameter interval is going to give us an initial point and a terminal point for that path once we plug it into r of t. Now we know from Newton's second law of motion, F equals ma. If r of t represents the parameterization of this path, we can think of this as the position function for that particle, which means r double prime would be the acceleration of that particle. So F equals ma can be written this way. F at this point, r of t, remember this represents a point on the curve, is equal to m times r double prime. Okay? So we know that we can compute, so this is a force, a velocity field. It's a vector field. I'm sorry, let me back that up. It's not a velocity field. It's a force field, which again, remember, is just a vector field where the vectors represent forces acting on a particle or an object. So in this force field, we can compute the work done by this force field on this curve C, moving this particle along this curve C, by using a line integral of the form f dot dr. So we're going to do that, and I'm also going to just notate this. The initial point, r of A, I'm going to call capital A, which we'll use a little bit later. R of B, I'm going to call capital B. These represent points, initial point and terminal point on our curve C. So the work is the line integral along C of f dot dr. We evaluate this line integral just using the standard, using the definition of this. So f is really f of r of t dot dr, which is r prime of t dt. Okay. Now up here we have a representation for f of r of t using Newton's second law. So this can be written as m r double prime of t dot r prime of t dt. Okay. Now we go from this step straight to this step, and it says Theorem 13.2.3, Formula 4, and it may not be immediately obvious where this is coming from. So this is the product rule that we came up with for dot products all the way back in chapter 13. And what I want to do is just on a separate piece of paper work this out and show you why this works. So if I wanted to go backwards, d dt of r prime of t dot r prime of t. If I was going to evaluate d dt of r prime dot r prime, from our product rule, we know that that's r, I could take the derivative of the first, which would be r double prime dot r prime, plus the derivative of the second, so r prime dot r double prime. But we know that the dot product is commutative, so I can switch the order of either one of these, showing that they're common terms, and write this as 2 times r prime dot r double prime, if I wanted. Okay, so you notice it's 2 times this quantity. Let's come back here. If I were to multiply that by 1/2 to cancel out the 2, that is accounting for why we have this m over 2 out here. Okay, so again, you could show that if we took the derivative of this, we get 2 times r prime dot r double prime. Here's r prime dot r double prime, and the 2 will cancel with this 1/2 right here. Notice the m was also brought out of the integral. Okay. Also, again, notice that my definite integral has limits of integration a to b, just using the standard way that we evaluate these line integrals. Okay, now the point of changing this into this form is I'm taking a definite integral of the derivative of a function. And notice this is a single variable function. The only variable is t. So the fundamental theorem of calculus is going to allow me to treat this function in here as the antiderivative of its derivative. right? So in a sense, the integration and the differentiation here will cancel each other, and it gives me a way of evaluating this integral. But before we do that, we know that if you take a dot product of a vector with itself, which is what's happening here, you get the square of the magnitude of that vector. So we're going to write this as the magnitude of r prime squared before we do use the fundamental theorem. Okay, so using the fundamental theorem, the antiderivative of this integrand would just be r prime of t squared, which is what we're seeing here. And then evaluated from a to b, it gives us this. Okay, now thinking of this in the context of the problem, or of the scenario that we're talking about, again, r is a position function, so r prime then would represent a velocity function. I can take these r primes and call them v, representing velocity. So what does that mean? Well, that means I can take this and just represent it this way. The work done moving this particle from that initial point A to that terminal point B is 1/2 m times the magnitude of the velocity at B squared minus a similar looking quantity but at A here. Now, this quantity is an important quantity in physics, and we have a definition for it. So to be a little bit more general, if I replace this A or this B with a T, then that quantity 1/2 m times the absolute value of the velocity at that time t is what we call the kinetic energy for that object. Okay, that's a matter of definition. If you've been through physics, you probably at least have or even if you haven't been in physics, if you've taken any science class, really any physical science class, you probably have at least a vague idea of what kinetic energy is in a physical context. So this is what our actual definition of this will be. If we give it this definition, then what this is saying is that the work done moving this object from point A to point B is just the difference between the kinetic energy at the terminal point of this path and the kinetic energy at the initial point of this path. It's the difference between those kinetic energies, and that's where we get our work from. Okay, so keep this result in mind. Now let's move on and make an assumption about the force field that's moving this particle along this path. We're going to assume here that F, our force field, is a conservative vector field. Now, it turns out, even though we've spent some time talking about conservative vector fields and showing that, you know, there's special criteria that they have to satisfy in order to be conservative, and a lot of vector fields are not conservative. It turns out then that a lot of the time, the types of force fields that arise in physics are naturally conservative vector fields. So making this assumption is not a big leap. Not as big a leap as it may feel. This is very, very typical of the kinds of vector fields we encounter in physics. So we're going to assume that our force field is conservative, which means it has a potential function, something that this is the gradient of. I'm going to call that potential function little f of x, y, z. Okay? We're going to make a new definition using this potential function, and we're going to call it the potential energy of the object. So the potential energy of this object at time t is just going to be interpreted as the opposite of this function, where the point in here corresponds to the position of that particle at time t. So p is equal to negative f, little f. Okay? Here's where we apply the fundamental theorem for line integrals. We haven't needed it up until this point, but we're gonna use it here. So the assumption that f is conservative means we're allowed to use the fundamental theorem. So if I wanted to calculate the work done on this object, which we've already done, but we're gonna look at it from a different perspective now. F dot dr, because the potential function for f is little f, that means that that capital F is equal to the gradient of little f, but that would be the negative gradient of p, because that's how little f and p are related to each other. They're opposites. So this f right here can be changed into negative del p dot dr. Okay? And remember, p, that's your potential energy function. So now, rather than evaluate this line integral directly like we did in the case up above, we just go straight to our fundamental theorem. This lets us evaluate the line integral by just taking the difference between the potential energy function at the terminal point minus the potential energy function at the initial point. Notice this minus here. Okay. So what does that mean? Well, if I use this minus to switch the order of subtraction here, this is telling me that the work done on this object is equal to the potential energy at point A minus the potential energy at point B. What we've done is we've calculated the work done on this object in two different ways, getting two expressions for the same quantity. So that means that this expression, representing work k of b minus k of a, is equal to this expression, p of a minus p of b, which I've written here. If I write this differently, subtract the k of b, add the k of a over, add the p of b over. Another way of representing this is that p of a plus k of a is equal to p of b plus k of b. I have a typo here, What this means is that the sum of the potential and kinetic energy at point A is equal to the sum of the potential and kinetic energy at point B. And we call this the law of conservation of energy because this sum here we usually refer to as the total mechanical energy of an object that's in motion. So even though the potential energy and kinetic energy of this particle might be changing as this particle, and it will be changing as this particle moves along this curve C, the combined energies never changes. It's always the same. Again, this is something that you're most likely familiar with from physics, if you've been through physics, or really any physical science class, but this is now using the machinery of line integrals to put this on a stronger mathematical foundation and give some real definitions to what we mean by this law of conservation of energy. The other reason we like to look at this application of line integrals is it gives meaning to the terminology we've decided on. The reason this law of conservation of energy is the reason we call these types of vector fields conservative vector fields, because they are the types of vector fields in which the law of conservation of energy will hold if you're making the connection between that vector field as being a force field. Similarly, this is also the reason we call little f the potential function of big F, because it gives us, after taking its opposite, the potential energy of that object. So that's really where this terminology is coming from. It's straight out of an application from physics. Okay, that's going to be it for 16.3.